Okay, so here's what I want to do. I want to sell you on the idea of using control theory as an interesting and extremely important application whenever you teach the Laplace transform in differential equations. It's tailor-made for the Laplace transform is tailor-made for doing control theory in what's called PID control. And so what I want to do is focus on a very concrete case. An incubator, like you would find in a biology lab, it's essentially a refrigerator or a heater that can heat or cool its interior. Some can heat and cool, both, I'm going to assume that. And it's supposed to maintain a very precise internal temperature, regardless of what the ambient temperature outside is doing. So it sits in a lab with a perhaps not so constant ambient temperature. The incubator has to maintain a precise internal temperature set by the user. And so it's non-trivial to figure out how do you maintain the internal temperature of the incubator if you have the ability to heat or cool it. It turns out it's not quite as straightforward as you might think, but it's a beautiful application of the Laplace transform. So this represents a lot of applications in engineering. A physical system that is governed by a linear ordinary differential equation. We're going to model it with Newton's law of cooling. And we want the system to behave in a certain way that we choose, even in the presence of what's called disturbances in the system. The ambient temperature in the lab changes, other things can change, and the incubator still has to maintain its precise internal temperature. One of the most common methods for controlling an incubator or any kind of technology is called PID control theory. It's very common in all of our technology, and it relies heavily on the Laplace transform. So it's perfect to use in an undergraduate course. So let's do this. To be very concrete, let's say that we have the ambient temperature of the lab is 70 degrees Fahrenheit, and it stays constant at that temperature. We want the incubator to stay at 80 degrees Fahrenheit. Now, if we don't have some kind of heating element in it, we know what's going to happen. It's going to slowly cool to 70 degrees, no matter how well insulated it is. So here's one strategy. If there's a heating or cooling element in this incubator, set it at a level, a constant power level, so that it precisely balances the heat loss to the environment. And it will run at that constant power level, and it will keep the incubator at 80 degrees. This is called open loop control. You just set it, you set the control element and let it do its thing. It pays no attention to the environment. It just runs at a predefined level. The incubator, in this case, will maintain its constant internal temperature as long as nothing changes. Now, let's do this. Let's write down a model for how the incubator might behave. Let's say it obeys Newton's law of cooling. There's good old Newton's law of cooling. I put in a constant ambient temperature of 70 degrees here. Y of t is the temperature of the inside of the incubator, and there's a cooling constant K here that I'm going to take it to be 0.05 in a moment, but it could be anything. And that governs the incubator's behavior without any control element in it. There's no heat source. We're going to implement a heat source in this fashion. I'm going to put what's called a control function over here, U of t in red, and that represents a heat source inside the incubator that can be used, or a cooling source if U is negative, and that can be used to control the incubator's temperature. So that's how we're going to implement control here. U of t is chosen according to whatever strategy we decide upon to make the incubator stay at 80 degrees. So let's take a cooling constant of 0.05. In this case, it would have units of degrees per hour. And suppose we start the incubator at the precise correct temperature, 80 degrees, the desired temperature, but we don't exert any control. We don't turn the incubator, we don't turn the heating element on. The incubator temperature looks like this. That's the solution with Newton's law of cooling. So 70 plus 10 e to the minus t over 20. The formula is unimportant. The graph is what's important. The incubator slowly cools down to 70 degrees. That doesn't cut it. We want it to stay at 80. So what we're going to do is we're going to turn on the heater via this control function in such a way that y of t equals the constant 80 is the solution to the ODE, the controlled ODE that you see there in red. So if you want to know what should I set U of t at to make that happen, plug y of t equals 80 into the DE, the control DE. And if you do that, y prime is 0, you fill in all the blanks, and U of t, you can solve for U of t. It turns out you should set the control function, the heater, at 0.5. In this case, it would be units of degrees per hour, if we're working in hours. That will keep the incubator temperature at 80 degrees precisely. There's the solution to the ODE under this condition. This is open loop control. The incubator will run at level 0.5 no matter what. But if something unforeseen happens, a disturbance, like somebody turns down the ambient temperature in the lab at time 20, here's what will happen. The control element runs along merrily at its predefined level. It does not recognize the ambient temperature is dropped, and this is what the temperature inside the incubator does. It slowly drops over time. This is where the lab temperature dropped 5 degrees at time t equals 20. Open loop control has its uses, but in this case, it would not be sufficient to control the incubator's temperature. Now, the problem is, of course, open loop control, it doesn't adapt to disturbances, unexpected changes in the system. In this case, it could, the lab's ambient temperature changes. Somebody opened the window, or someone opens the incubator door to get something out or put something in, or the incubator load changes, fewer or more samples are put inside, and that could change the behavior of the incubator, or the incubator itself changes over time as it ages, door seals leak, etc. Open loop control doesn't recognize any of this, and it doesn't recognize that the temperature of the incubator is off target and it can't correct for it. What we need is some kind of algorithm that can take measurements of the internal temperature of the incubator and say, it's running too hot or it's running too cold, and then compensate on the fly. This is what's called feedback or closed loop control. Now, this kind of control is absolutely ubiquitous in our technology. In a car, think about the cruise control in your car. You set it at 60 miles an hour, and your car ideally stays at 60 miles an hour, regardless of whether you're going uphill or downhill. The control will recognize that the speed is off and increase or decrease engine power. Also, there's control algorithms galore in how the engine operates, in how the transmission operates. There's feedback control everywhere. It's used in all modern aeronautics. Almost all modern aircraft use some kind of control to stabilize the aircraft, augment pilot input. Electronics, since time immemorial, has used control for voltages, frequencies, currents, that sort of thing. And modern and mechanical systems like vibration tables use active control to actively counter vibrations and hold the table steady. So what we want to do is implement feedback control for our incubator. One simple strategy that almost anybody would hit upon is what's called proportional control. In the context of the incubator, if the temperature is running too low in the incubator, it's running at below 80 degrees, and you want it to be at 80, it's too cold, turn up the heat. If the incubator is running too hot, turn on the cooling element and cool it down to 80 degrees. This is called proportional control. And what you do is you take the control function in the DE that I presented earlier, I'll present it again, and you take the control function to be proportional to 80 minus y of t. K sub p here is some constant, positive constant, called the proportional gain. If y is running too low, U of t turns on positive, and the heating element tries to warm the thing back up. Conversely, if y is too high, U goes negative, and it cools it back to 80. Now, notice that U of t doesn't care what the ambient temperature is. It just says, am I on target for the internal temperature, and corrects. Well, here's what the ODE with this control function, and it looks like y prime equals minus k, Newton's law of cooling. With that control function, when you plug that in, here's what you get. You get a new ODE that's Newton's law of cooling, but with this control function built in. And notice, it's still a simple linear constant coefficient ODE. K sub p is a known constant. Y of t is the unknown. You could solve this ODE. At this point, you don't even need Laplace transforms. You can do this in any DE course. And it looks like a very simple, very logical way to control the incubator, but it has a surprising shortcoming. Here's what the situation looks like if you implement this proportional control. So what I've shown here is, in blue, is the open loop control from a few slides ago, where the heating element runs at a constant level, but at time 20, the lab temperature suddenly drops. And you see the graph in blue there. It's perfect up until time 20. It's at precisely the correct level to counter the heat loss up to time 20, but then the bottom falls out and the blue curve drops down toward about 75 degrees. But look at the red curve that implements proportional control. It suffers much less when there's this disturbance in the system at time 20. However, so it stabilizes at a value that is about 79.3 degrees, not 80 degrees as you might hope. And indeed, look at how the proportional control curve behaves even before a disturbance takes place. Up to time 20, the proportional control is still not hitting the mark. It stabilizes at about 79.5 degrees. So proportional control, it looks simple and logical, but it stabilizes at a biased value that's not the 80 degrees we hoped for. Still, it's only a half a degree low. It's better than open loop if there's a disturbance, but proportional control, surprisingly, at least at first blush, doesn't quite work. So what we're going to do is we're going to modify proportional control. And so far, we're still completely in the realm of linear, constant, first order differential equations that you could do almost in a calc class. You could do this in a calc class. Okay, in proportional control, things stabilize at a value that's too low, even when we're at a biased value. And you can actually analyze that. You can have students analyze that and say, okay, what will it stabilize at? Well, here's the DE that implements proportional control. You can work out what's the steady state solution to this differential equation. What constant value will it stabilize at? Well, you work it out, and you can work out that in this case, the steady state solution is 80, the desired set point, as it's called, minus this term here in red that's a bias that is not 0 unless Kp is, well, arbitrarily large. In this case, when you fill in Kp equals 1, as I did for that particular example, you'll find that the thing stabilizes at 79.5 degrees, and that's not what we want. We want 80 degrees. Now, if you look at this bias term here, you can make it as small as you want by taking K sub P arbitrarily large, but the problem is that might overload the control element, because K sub P is what moderates how high you turn on the heater, depending on what the temperature in the incubator is doing. If K sub P is extremely large, it might try to set the heater at a level that's simply not feasible. So this is not an ideal solution, making K sub P very large. So we're going to take an alternate tack. We're going to implement what's called proportional integral control, or PI control for short. This is where the Laplace transform is really a godsend, because PI control looks like this. The control function that controls the heater looks like that term in blue. That's the proportional control we implemented a moment ago, plus a term that looks like the thing in red there, and that's effectively the proportional control all over again, except this time it's being integrated from 0 to t. So the effect that has is, imagine the temperature Y of t drops below 80 degrees. The proportional term kicks on and says, turn the heater on. Well, we know it won't turn it on at a level that sustains 80 degrees. The integral term will come on as well. And as time goes forward, if the temperature remains too low, this integral term keeps winding up and cranking up the heater until the thing stabilizes at some new value. The question is, what will it do? What will the solution to the Newton's law of cooling do with this control function in there? Well, you take this control function here and you jam it into the control DE that was Newton's law of cooling. Watch what happens here. So the Newton cooling ODE ends up looking like, there's another term here, y prime equals, this is the usual Newton's law of cooling. Here's the proportional control. And there is, in red, is the integral contribution to the control function. And what I have just written down there is an integral differential equation for y of t. Now, this is not a standard thing to do in an undergraduate course, and it looks scary. I put that here. It looks scary. What am I supposed to do with that monstrosity? Laplace transforms make this easy to analyze. In fact, I can't believe I went so long without introducing students to any equations like this. If you Laplace transform that equation, it's easy because this term in red here is a term we usually teach students how to Laplace transform. If you Laplace transform this integral differential equation, it becomes an algebra problem, just like the usual differential equations we treat with the Laplace transform. This term right here in red has a standard Laplace transform. The problem of finding y of t that satisfies this integral differential equation has become an algebra problem of solving for capital Y of s. Once you fill in the various constants that we know and you fill in the initial condition. Now, in our particular example, where the ambient is a constant 70 and the desired temperature is 80 degrees, and Ki and Kp, I take Ki and Kp to both be 1 just for simplicity, and initial condition 80. If you fill in all that stuff and you can solve for y of s, and you get this, that is the Laplace transform of the solution to that integral differential equation there. This is what the system will do. That's the Laplace transform of how the system is going to behave. And now you can just do an inverse Laplace transform on this. And this is what the temperature of the incubator is going to do. This is assuming there's no disturbance in the system. Now, look at what happens. Look at how it behaves. Here's the solution plotted in the time domain as a function of t. The system starts at the desired 80 degrees, and there's no disturbance. Everything is going according to plan. Even though there's no disturbance, it does do a momentary couple-hour drop about a quarter of a degree. And this initial 1 hour or so is where the proportional term is dominating the control. But then the integral term begins to wind up, and it says, no, you're dropping too low. Come back up. And notice this control function here, this strategy, does in fact stabilize the system at the desired 80 degrees. Now, that's with no disturbance. What if there is a disturbance in the system? What would that control cause the temperature to do? Well, there it is. I won't show you the formula, but it's easy to solve. With the control in operation and a disturbance at time 20, where the ambient temperature in the lab drops 5 degrees, this is what the incubator temperature will look like. Again, it does the same thing it did in the previous slide up to time 20. And then suddenly at time 20, the lab temperature plummets 5 degrees. The temperature in the incubator begins to drop, but the control algorithm recognizes that it only lets it drop a little over 1/10 of a degree before it winds back up and turns the heater on at a higher level to stabilize it at 80 degrees. And again, despite the fact that it involves solving an integral differential equation, in the Laplace transform domain, it's as easy as a differential equation. So this is an example of PI control and how you can analyze it with the Laplace transform. Now, so there's lots of ideas lots of things you can do in class with students with this that are totally accessible in an undergraduate ODE math course. PID control is where you implement in the control function the derivative of the incubator temperature. You throw that into the control mix, and that can let you do certain things that you can't do with P and I alone. And so you can have students analyze that. K sub d there is some constant called the differential gain. Another interesting experiment is what if in the incubator you change the set point of 80 degrees. Maybe you decide you want the incubator now to be at 80 degrees for a while, and then you want it to go to 90 degrees. So you turn the dial on the side up to 90 degrees. How will the controller respond to that? How quickly will it get to the new desired temperature? Will it get there? Will it overshoot? Depending on how you choose the parameters in the control algorithm, it may or may not do what you want very well. For example, if you do it foolishly, the controller can actually make the system unstable. For example, even in simple proportional control, the first thing you can do is have students try setting the proportional gain negative. Tell the controller that if it's running too hot, turn the heat up. Okay, that's a disaster. It causes an exponential runaway in the temperature inside the incubator, at least until the control element can't do it anymore. So stability analysis is a very interesting topic here. And more generally, how do you choose the parameters that govern the control function? There's an entire cottage industry in engineering devoted to what's called controller tuning. How do you pick these values? There are all kinds of strategies that you can look at, and it's fun to experiment with this and see what happens. And all of this stuff in engineering is done almost entirely in the Laplace domain. You use block diagrams, transfer functions. Some of us do that in ODE courses. We talk about system transfer functions. And this topic really brings to light the value of viewing the Laplace transform as a function of a complex variable. That gives you even more insight into how this process behaves. Not hardcore complex analysis, just the Laplace transform is a rational function of x. Where are the poles of that function, the zeros of the denominator? That can tell you a lot about how the system will behave when you implement it. And in the new, not to just plug the book, but in the new SIMIODE text, we've got some fun applications of control theory. For example, controlling a vibration isolation table, or balancing an upside down pendulum, or equivalently, how do the Segway scooters keep themselves upright? Okay, there's control algorithms there that respond to the user's input, of course, but also prevent the user from falling on their face, ideally. So that's my cell for implementing a little baby control theory into an ODE course when you do Laplace transforms. So, thanks.
Yay! I do something different with Laplace. I introduce it in week 4, just with really basic things. So then when we get to the end of the semester, and instead of saying, oh, there's a whole different way of doing solving differential equations, I've already introduced it early. So then I could give them it's silly to be doing it now because there's easier way to solve first order differential equations, but getting them used to the concept. Then when we move to the harder stuff, they're not still struggling with the whole concept of a Laplace transform. So I think I'm going to use this as a teaser for next week on why the heck we're gonna do this.
It's a huge area of engineering, so that's why I can't believe. I mean, given that I'm at an engineering school, I can't believe I never thought of doing this until a couple of years ago. And the engineers, so many of our students go from our DE course immediately go into engineering courses where they start doing this. So it's nice to give them a taste of it ahead of time.
Excellent.
And this is one application where, I mean, when you do DEs, when you say to students, oh, we can solve DEs with Laplace transforms now, it turns it into an algebra problem. That's true, but in some sense, it doesn't really make solving them any easier from the algebraic standpoint. But for the control theory applications, you can't do it without the Laplace transform so easily. There's no other way to do it.
Excellent. So do we have any questions? People can either enter questions in the chat, and I'll say them out loud, or you can turn on your mic and just hop right in.
Hi, Kurt. This is Susan Schneider. Thanks. This is great. And it's great not because I teach differential equations, but because I teach engineering systems. And we spent a whole bunch of time talking about thermal systems. You've just fed right in because we don't do control. We just analyze them. Now we can sneak in. Now I can sneak in a little bit of control, which is great because I also teach the control classes.
Oh, okay. Well, cool.
Great
Good.
idea. Thank you so much.
Sure.
This is Jeff Denny. I have tried creating a worksheet where they slowly built kind of using, I backed into the PID controller by using a spring idea of car following.
Oh, yeah.
And actually it ended up being great fun. And unfortunately for them, and in the end, they just kind of were tuning it and playing with the parameters to try to figure out what worked best.
Yeah.
It worked okay. I think I need to explore a little bit more, doing more Laplace transform on it with them. But at the time, it was a good experiment. And like you said, something I've been impressed by is our engineering students come back to me semesters later and say, man, we still use that every day. You wouldn't believe how much we use that. So,
oh yeah. I think it's the most common basic control strategy in engineering is PID.
So it's been a good experience. Next time I teach it, I hope to expand it some more. So thank you for doing this.
Yeah, you're welcome. Anyone else?
Any other questions? So look at this. We're all sitting here with our cameras off with black squares and white names, just like we get annoyed with our students for doing. So let's at least all for a moment turn on our cameras so we can wave and say hello. And as we're doing that, maybe we'll have a couple more people having questions. And I assume, I don't remember, are all these the PowerPoints and whatnot going to be available to people afterwards?
I'm happy to send them to anybody and everybody. And of course, they said they were going to video all this stuff too. So
yes, this is being recorded. I don't think the recordings will be released immediately, at least not to people who paid for the conference. We're keeping the recordings inside our little circle. But yeah,
I'll be wants them, just send me an email. I'll send you the slides.
I'll be sending you an email.
Okay.
All right. Any other questions?
Oh, we got chats here. Oh, okay. Yeah. Oh, okay. Yeah. Thanks. Anybody who wants them, I'll send them along.
Well, do you want to type your email into the chat, and then that way we can just email you instead of making you work for us?
Yeah. Email me. There I am.
I have a question.
Yeah.
What control theory textbooks do you recommend for self-study?
Oh gosh, that's not really my area of expertise so much. I mean, I know basic control theory. I don't have a book that I use though. I just learned it all by osmosis, I would say. So I don't know. There might be somebody else who has an idea on that. Not I though.
Okay. Thank you for the presentation.
You're welcome.
All right. Well, I think we have a scheduled 5-minute break between sessions. Let me double check that. Yes. So we're not supposed to start the next one till 4:35. We're trying to work in breaks, so if people have to step away for a moment, it's okay. You're not going to miss anything. Did you put your email address in the chat?
I did.
I don't see it yet.
Yeah.
Oh, well, that's odd. I just typed it in. Maybe it was only in response to here.
Did you put it in the Zoom chat or in
make sure
I put it in the Zoom chat.
Make sure it says to everyone, because it doesn't always default that way.
Oh, you're right.
Can you tell I teach with Zoom?
Thank you very much.
There we go.
Perfect. Thank you. So anybody who's interested in a copy of the presentation, go ahead and copy Kurt's email. Thank you very much, Kurt. We appreciate you doing the opening talk.
Thanks for coming, everybody.